Hi everybody, thank you for inviting me to this valuable presentation. Thanks to the Technology Collaboration Program for this opportunity to show our work. My name is Camilo Franco, and well, I am going to show you a little bit and talk to you a little bit about nanotechnology, biotechnology, info, convergent technologies applied to the chemical enhanced oil recovery. So the title of this talk is Converging Technologies Applied to CEOR Processes from Laboratory to Field Applications. This is an agenda for this talk. First, a brief introduction, then I will talk about interval tracers, after polymers, surfactants, modified capillary number, and current strategies to have a better understanding of the CEOR processes in the oil and gas industry. So, starting with the introduction, I'm going to read a brief paragraph from a paper we published last year, and that is nanotechnology is a crucial player in the fourth industrial revolution as part of convergent technologies, alongside with biotechnology, information technology, and cognitive science that will lead humanity once more to break barriers and address challenges, mainly reducing the gap of what we can do and the way to do it responsibly. Okay, so what we were trying to say here is that nanotechnology, biotechnology, information technology, and cognitive science are crucial as convergent technologies where the matter will lead to the human development and to the rethinking on or a new perspective of how can we do things in a more environmentally friendly way or with lower energy resources, but the way of different technologies that can proportionate a clear vision of what we can do for the oil and gas industry and for the human development. So the four pillars of the convergent technologies are the information technology, the cognitive technologies, the biotechnology, and of course the nanotechnology. So where these four technologies converge to one state of the matter, it will lead to the human development in a more sustainable way. In this sense, for enhanced oil recovery processes, mainly chemical enhanced oil recovery processes, we can have different challenges or problems during polymer or surfactant injection. For example, in the case of conventional surfactant injections, you need to use ultra low interfacial tension, or in the case of polymers, you need to increase the viscosity of the water with high polymer concentrations that can lead to some formation damage. Also, polymer can degrade by several mechanisms, including temperature, salinity, oxygen, and this will be a problem because as a function of time, we will be injecting water in the case that degradation is not inhibited. Also, both surfactants and polymers can be absorbed or retained in the porous media, leading to the waste of valuable additives during the polymer or surfactant fluid. Also, in many of these cases, these products are not injected as one batch, but for instance, you can inject a polymer with surfactant or polymer with alkali and surfactant, but it is rarely seen that you can inject only polymer or only surfactant, which include high dosages and costs, and of course, in many of the cases, the need of raw facilities, for example, for the preparation of the polymer solutions. The way that convergent technologies can help these aforementioned mechanisms that cause problems during the chemical injection is that nanoparticles and biofluids and cogno and info science can lead to the strategic development of systems that can, that can lead to a target delivery, for example, of the surfactant at the oil-water interface. So you can use different type of nanoparticles, for example, like nanocapsules or raw nanoparticles that deliver the surfactant just where the surfactant is needed. Then avoiding the absorption of the porous media, there is no longer a requirement of ultra-low interfacial tension. You can work with, in fact, low interfacial tension, and the field trials have validated this. Also, you can look for only the biofluid or bionanofluid injection instead of SP or ASP. For example, I will show you two cases of nanofluid injection without any polymer, which can lead to cost reduction and low dosages, and the avoiding of complex equipment or facilities for the injection. Okay. So first, I would like to start with integral tracers in a brief way, because for performing a successful injection process, you will need to check the traceability or the interwell connectivity in the reservoir between the injection and producer well. So typically, different kind of tracers, radioactive, fluorobenzoic, are injected, and the time and cost could be long and high. For example, here in Colombia, you can have one sample, and the result of the traceability of that sample can last up to 2 months. Meanwhile, with the development of these tracers that are like bionanotracers, synthesized from from a fruit that is typical from Colombia, you can have carbon quantum dots that are fluorescent nanoparticles, and with a fluorescence spectroscopy, you can track the nanoparticles in the producer well. In this case, you can have the result even as low as 3 days, as showed in the field trial. These results you are seeing here from 2018 and from the first field trial held worldwide. And we were able to trace the the nanoparticles even from the third or fourth day, and it was made in the field facilities. So there was no need to send the sample, to ship the samples to robust laboratories. Instead, in this case, we saved some time by doing the analysis just in the field. This is a good option, because as we are working with quantum dots, the next step or the next challenge is to work with 3, 4, 7, 10, the different colors that are necessary for checking, for example, different injection wells that can lead to one producer, or for example, the injection through different sands or different porous medium, in which you can have an early disruption of the water in the producer. So there is this strategic challenge, and the way that these carbon quantum dots, bio nanoparticles, can help to reduce costs and reduce time for interpretation of the results is a lot of work and experience that has to be done in the field. Regarding polymers, there are different mechanisms for which polymer and nanoparticles may work. You can use different type of polymers. In fact, different biopolymers can be injected to have an enhanced inhibition of degradation under, for example, salinity or temperature. But the main concept here is that nanoparticles are able to generate a specific viscoelastic network in the presence of polymer. So in this case, you will have different mechanisms, microscopic mechanisms that will lead to the enhancement of the recovery. But it is important to say that it is a synergistic effect between the polymer and the nanoparticles. This is one example of how the viscosity of a polymer solution, it is about 1000 ppm, can increase as a function of the particle concentration. because of the strength of the polymer network. Okay, and it is not a result of just adding nanoparticles, because as you can see in the figure in the right, when you add the different concentration of silica nanoparticles in water, you don't have a clear increase in the viscosity. But when you do it in a polymer solution, you see it. And this is consequence of the interaction between of the polymer and the nanoparticles. And we have seen that the absorption of the polymer over the nanoparticle surface can be a key player that can enhance this interaction. Another factor is the interfacial tension that is also reduced. It is not at the level of, for example, a surfactant fluid process, but it certainly can cause an increase of the recovery factor and increase in the capillary number. That, together with the contact angle measurements, corroborate that the synergy between nanoparticles and polymers can lead to a more efficient process. Also, as you can see, this interaction can inhibit the retention of the polymer system over the porous media. Here we have S-type curves, retention curves of polymer as a function of the pore volume injected, and the gap between these two, between these two curves, the red one and the one with the blue dots, it will be the amount of polymer that is retained in the porous medium. So as you can see in the figure at the right, the gap between these two curves when including nanoparticles is less. In this case, indicating that the retention of the polymer over the porous media, over the rock surface, is lower in the presence of nanoparticles, which can lead to a more stable system that can last for a longer time in the porous media and enhance the recovery. We found, as you can see in the figure in the left, a clear relationship between the surface acidity of the nanoparticles, the degradation of the system, in this case measured by a rheological parameter related to the viscosity of the system, and another parameter, this H parameter, related to the affinity of the system. The H parameter indicates that if it is high, the system has low affinity for the nanoparticles. Okay, so as you can see, as the surface acidity of the system increase, the H parameter increase, and for example, um, the for example, the degradation of the system decreases. In this case, it can be a direct relationship between the acidity of the nanoparticles and the degradation of polymer solutions. And in the figure in the left, you can see different viscoelastic modulus, which are measured at 0 day and 15 days in the presence and absence of nanoparticles. And the results indicate that there is stabilization and inhibition of the degradation of the system, because the gap between the curves for 0 and 15 days is lower in the presence of the nanoparticles. This was then corroborated through the measurement of the relative permeability curves for both system with and without nanoparticles, in which it can be seen that the water mobility is greatly reduced, and this is because the effect of the nanoparticles by altering the wettability of the system and generating a disjoining pressure that will release the oil from the porous media. And then corroborated with the oil recovery curves with different concentrations of nanoparticles. I need to say that there is a current challenge in which polymer solutions with nanoparticles studies need to lower that concentration, because in most of the articles, high concentrations, even up to 1% or 2%, I have seen 5%, it's too much for the injection. And it should be corroborated that this amount of nanoparticles and also the type of nanoparticles will not cause any formation damage. So there is the challenge of going through low nanoparticles concentration, for example, 10 ppm, 30 ppm, maybe functionalized nanoparticles that can lead to a more efficient system. And also, we made the displacement test with the system in the absence and presence of nanoparticles, but after 15 days of degradation. In this case, as you can see, after 15 days, there is a clear difference in the oil recovery between the nanoparticles and the polymer solution, indicating that there is an inhibition of the degradation of the system. In the case of surfactants, there is a concept in which wearability, interfacial tension, and the absorption of the surfactant over the nanoparticles and the porous media should be included. So all these measurements can lead to an enhancement of the process. In this case, the nanofluid can reduce the contact angle, increasing the system wettability to a water-wet state, reduce the absorption of the surfactant over the porous media, and also lead to a stable low interfacial tension. In this case, it is really important to have the injectivity evaluation. It is like you are injecting like 100 per volume of the nanofluid to check that the amount of nanoparticles, as I told you before when we were talking about polymers, that the amount of nanoparticles is suitable to not cause any blockage problem because the high amount of material that you are injecting in an enhanced oil recovery process. This is something that all studios need to include to check the stability. But once you do it, the injectivity evaluation, you can state that the oil recovery in the presence of the nanoparticles and the nanofluid will be greatly enhanced by the inclusion of the nanomaterial. This is one example of the field trial that is being conducted here in Colombia. It has been expanded to several fields, and for example, in heavy oil fields, in light oil fields, this was the first field trial. You can find the information in the reference below. And the surfactant injection was varied for different concentrations from 1000 to even 300 ppm, the nanofluid injection. And there was a rapid response of the system in the producer wells, and there was a great success because the high cumulative incremental production in the system in both patterns. So there was a study of the effluents obtained from different fields, and it was find a great relationship between the productivity and the capillary number estimated from the effluents. It means that we took the produced water and the produced oil and we checked the interfacial tension, the wearability of the system, the viscosity of the injection water, and there was a direct relationship between these properties, the capillary number and the productivity of the wells. This was also observed in the well B, and this indicates that the methodology and the way that the nanofluid has been injected can be even predicted as a function of the capillary number obtained. For this, we implemented a strategy from machine learning in which we took the viscosity of the system, the capillary number, the type of the well, the type of the crude oil, and we found that with 18 tests, 72 training system, and 90 datasets, it was enough to have a clear model that can predict the oil productivity using nanofluids in an enhanced oil recovery process. Also, we have developed different biofluid systems from different waste from fruits here in Colombia. It can increase grade the oil recovery, and the fact is that nanofluids can have an enhanced degradability, and it can be lead to a more sustainable way of injecting nanofluids. And finally, we have a modified equation for the capillary number, in which we include the reduction of the absorption of the porous media and the effective interfacial tension that we will have in the system. This is the equation in which we make a correction of the interfacial tension that taking into account the concentration of surfactant that actually is going to reach the oil and water interface. And we have found that doing several tests of oil recovery capillary number, there is a direct correlation that fits all the previous capillary number equations that have been implemented. Current strategies include the development of human talent, open access information, and conference with open access, decarbonization processes during CEOR and graduate courses. Thank you very much, and I hope that you like the presentation. I am open to any questions.